AC circuits, we're going to talk just basic series AC circuits. By AC we mean a circuit that has alternating current. So the source, the voltage source, is alternating. We're looking only at the sinusoidal type circuits. To represent the power source, since it's not a battery, it's not a constant potential difference, we use a little circle with the sign squiggly in it. We're going to look at all three elements that we talked about in a circuit. So a resistor, an inductor, and a capacitor. For the resistors, since the current will be alternating with time, the voltage drop across the resistor will also be alternating with time. The voltage drop across the resistor depends upon the current flowing through it and the resistance. So that's no different from what we've talked about before. The difference is that I is changing. I is a sinusoidal function. It's changing with time. Therefore, the voltage drop across the resistor is changing with time. Now, we will be most interested in either the maximum value of the voltage drop across the resistor. The maximum voltage drop across the resistor is going to depend upon the maximum current that flows through the resistor times the resistance. Or we may be interested in the RMS value. So just like with the electric field and magnetic field, we're going to talk about RMS as if it were an average. It does tell us kind of on an average what's happening for our element. Just like for the electric field, the RMS value of a voltage drop is equal to the maximum value over the square root of 2. So the relationship between RMS and max is the same as it was before. And that's going to be true for the current as well. Since these are sinusoidal functions, the true average is going to be 0. But on average, there's nothing happening. That's a little confusing. There are things happening in the circuit, and therefore we do talk about the RMS value. Now our equation up there, the delta V for the resistor is equal to IR, will work for RMS values as well. The RMS value of the voltage drop depends upon the RMS value of the current times the resistance. So the delta V and the I can be either both maximum values or both RMS values. And the equation still holds. Now with the resistor, the current and the voltage are in phase with each other. So when the current's maximum, the voltage drop across the resistor will be maximum as well. And when the current's 0, the voltage drop across the resistor will be 0 as well. Resistors convert energy from electrical form to heat to light. So we still talk about power. The power dissipated, we're just going to look at the average power dissipated through our resistor. The average power dissipated depends upon the RMS current and the resistance. You can write it in terms of the voltage drop across the resistor as well, if you want. But you have to remember that it's specifically the voltage drop across the resistor that you need, because it's the resistor that's transforming the energy. So resistors behave the same way they've been behaving all along. The inductor will be trying to oppose the changing current. since the current is constantly changing, since it is an AC source, the inductor is constantly trying to oppose the change. The voltage drop across the inductor is going to depend upon the frequency of the source. The frequency is going to matter. The frequency, the rate at which the source is alternating at. The faster it alternates at, the bigger response the inductor has. Because the inductor is really trying to oppose that change. The smaller the frequency is, then the less of a response the inductor will have. We're going to use what's called the inductive reactance. Inductive reactance is a measure of how much resistance that inductor supplies to the circuit. Inductive reactance depends upon our frequency. It's specifically our angular frequency and the inductance itself. So omega, angular frequency, so units of radians per second, and L being the value of the inductor.
So what is it? Inductive
reactance. So inductive reactance is what it's called. The bigger XL is, the more resistance that inductor is behaving as a big, as if it were a bigger resistor. Now it turns out the voltage drop across the inductor and the actual current in the circuit are not in phase with each other. The voltage and the current are 90 degrees out of phase. The voltage is actually leads the current by 90 degrees. So as if the inductor is at a maximum, the current's at 0. If the inductor's at 0, if the voltage is at 0, then the current is a maximum. But we have a simple relationship that relates the maximum voltage drop across the inductor to the current and the inductive reactance. It looks very much like Ohm's law. Delta VL is equal to I times X of L. The units of that inductive reactance, the units of XL, are ohms. So the bigger XL is, the bigger the voltage drop will be for any given current. This equation works for RMS values as well. So you can either use both max values for voltage and current, or you can use both RMS values for voltage and current. So the inductor, if the frequency is high, if omega is really, really big, XL gets really, really big, and it basically slows the current, decreases current. At a really high frequency, an inductor in an AC circuit acts as if it's an open circuit. It pretty much stops current from flowing. If frequency is low, then the inductive reactance is small and you get current flowing through. So it acts more like a short. For capacitors, we're going to use what's called the capacitive reactance. You use X again, but a subscript of C. Capacitive reactance also depends upon frequency, but we get this inverse relationship. X sub C is equal to 1 over omega C. What that means is if frequency is high, XC is small. So the capacitor and the inductor are opposite of each other. If frequency is high, the inductor has a really high resistance in the circuit, and it acts as if it were an open circuit. A capacitor, if the frequency is really high, the X sub C is very small, and it acts almost as if it were short. If you think about it, the capacitor is going to be trying to charge up and discharge. If the current is flip-flopping too quickly, the capacitor is not going to have time to charge up at all. And so that's why XC gets smaller. We have a similar relationship for the voltage drop across the capacitor. So the voltage drop our capacitor is experiencing will depend upon the current and then X sub C. Now, please keep in mind, for both inductors and capacitors, the maximum value of the voltage and the maximum value of the current do not happen at the same time. These are not time-dependent equations. These relate the maximum values and they'll relate the RMS values, but they will not tell you the value of the voltage at any point in time. And that's because the current and the voltage are not in phase. For the inductor, the voltage is ahead of the current by 90 degrees. For the capacitor, the voltage is behind the current by 90 degrees. So it lags behind. So basically, they're not in phase. So these equations are not time dependent. But that's okay. They're still very useful in determining on average the RMS values, what's happening, or maximum what's happening. So they're all quite helpful. Now, Kirchhoff's loop rule still has to apply. Our voltage is going to be changing with time. We can write it as either a sine or a cosine function. It just depends upon the starting point. The source voltage, that whatever's being put in by the source, has to somehow be shared among the individual elements at any one point in time. So if you add up the voltage drops for each element, then at any one instant in time, they're going to equal the source voltage. But that's not true if you wanted to say the maximum voltage will not equal the maximum resistor voltage plus the maximum inductor voltage plus the maximum capacitor voltage. That's not true. So Emax does not equal delta VR max plus delta VL max plus delta VC max. And that's because all the elements do not have maximum values at the same time. They're out of phase with each other. And also, if you wanted to replace all those maxes by RMSs, it wouldn't be valid either, because they're not going to have their RMS values at the same time. So Kirchhoff's loop rule is valid at any instant in time. But since they don't have maximum values at the same time, they will not add up to give you the maximum voltage. In fact, if we found the maximum voltages for each of the elements, they're going to add up to be more than the source maximum, usually. Okay. So the question is, how do we look at this as a whole circuit? It's not like resistors in series where we can simply add up the resistance and have a total resistance of the circuit. It doesn't work that way because of the in and out of phase business we've got going on. So for the whole circuit, we're going to be able to say the maximum source voltage is equal to a maximum current times the overall resistance of the circuit. The overall resistance of the circuit we call the impedance, and we use a capital Z to represent it. So capital Z is called the impedance. You can think of it as the overall resistance in the circuit. It's going to depend upon the resistor, inductor, and capacitor. But it's not simply the sum of just the resistor, the inductor, and the capacitor. This equation is going to work for RMS values as well. So we need to figure out what Z is. And the way we do that is by way of what we call a phasor. A phasor is basically a vector. Imagine this being a vector. A phasor is a vector that rotates around. The length of the phasor represents the maximum value of whatever you're looking at. So for example, our phasor could represent the maximum voltage drop across the resistor. Now I want you to imagine we had a spotlight shining on this, and as it rotated, it's going to project a shadow on the whiteboard. What will happen to that shadow as this thing rotates?
Smaller.
It's going to get bigger, smaller, it'll go down and up.
Fine.
Yes. So imagine the spotlight coming from the right here. Here's our phasor. That shadow on the screen is the value of the voltage at any instant in time. So if this phasor itself represented the maximum voltage drop across the resistor, this shadow on the screen would represent the voltage drop across the resistor at that instant in time. As that phasor rotates, it rotates at a rate of omega t. As that phasor rotates, the size of the shadow is going to change, which means the value of the voltage drop across the resistor is going to change with time. As it continues rotating upwards, the shadow is going to get longer and longer and longer. As the phasor continues on into the second quadrant over here, the shadow will get shorter and shorter and shorter. When the phasor is perfectly horizontal, there will be no shadow, so that would be an instant when the voltage drop across the resistor was 0. As it continued going, the shadow would be pointing downwards and get bigger and bigger and bigger. So the voltage would be getting bigger and bigger with the negative polarity. So to figure out the value of Z, we actually need to do a little vector addition with our phasors. Now I'm going to choose one instant in time to work with. And I'm going to choose the instant in time when the voltage drop across the resistor is 0. Just because I want to. And it makes things easier. So the maximum voltage drop across the resistor will be along the x-axis in this case. This is just one instant in time. With the inductor and the capacitor, to draw them onto this picture, the inductor's voltage, well, I guess I first should say, please keep in mind the voltage drop across the resistor is in phase with the current that's flowing through the circuit. The current and the voltage for the resistor are always going to be in phase. So if I was to draw a current phasor, it would be along the same line as this delta V for the resistor. With the inductor, the voltage drop across the inductor leads the current by 90 degrees. So if I wanted to draw the phasor that represented the voltage drop across the inductor, it would have to point straight up, because it's 90 degrees ahead of the current, which is in phase with the resistor. The capacitor, the voltage lags the current by 90 degrees, and so when we draw in the voltage for the capacitor, we need to go down. Now, how long they are going to depend upon XL and XC. I'm just randomly choosing delta VL to be longer than delta VC. That doesn't have to be the case. Delta VC can be bigger than delta VL. To figure out on a whole what's going on, we need to add these three vectors vectorially. So if I add delta VL and delta VC, since this guy's coming down, we get that little piece. Add on delta VR, the result, right here, the result represents the maximum source voltage. So if we add them vectorially, the resultant vector represents the Emax, the source voltage maximum value. Now we have a really easy relationship between these. This is a right triangle. This side's the maximum voltage drop across the resistor. This side is the delta VL max. Now, if we write it just in terms of magnitudes, it would be minus delta VC max. So using the Pythagorean theorem, Emax squared will be equal to delta VR max squared, the one side squared, plus the other side squared, which is delta VL max minus delta VC max quantity squared. That's the relationship between all the maximum values. Now that's in a series circuit. And that's what we're talking about, is a series circuit. We can make some substitutions here. The maximum source voltage is equal to Imax times Z. So we're going to get Imax squared, Z squared. The maximum voltage drop across the resistor, looking over there, that's equal to Imax times R. Voltage drop across the inductor is Imax times X sub L. Voltage drop across the capacitor is Imax X sub C. That quantity needs to be squared. This term we could factor out the Imax squared. So the Imax actually cancels. And we find that Z squared is equal to R squared plus the quantity of XL minus XC squared. That is our overall impedance of our circuit. The impedance is basically the overall resistance that the circuit is supplying because of the different elements that are in place. Now, keep in mind, if you only had, say, a resistor and an inductor, no capacitor, you would just take the XC out of the equation. If all you had was a resistor and a capacitor, you would just take the XL out of the equation. If there's no inductor, you don't have XL. If there's no capacitor, you don't have XC. So forth. Okay. So the current is in phase with the voltage, the resistor's voltage. So by having inductors and capacitors in the circuit, we actually can end up with the phase shift between the maximum voltage and the maximum current. Phi right there. We can easily solve for phi. Tangent of phi would simply be delta V L max minus delta V C max over delta V R max, which if we make the same substitutions we did down here, all the currents will cancel, and we find that the tangent of phi is equal to XL minus XC over R. If XL is bigger than XC, our voltage max ends up in this first quadrant. We end up with the voltage leading the current by whatever angle that happens to be. If XL is less than XC, then this voltage would have ended up in the fourth quadrant down here, and we'd end up with a negative phase angle. So positive phase angle means voltage is leading the current. A negative phase angle means the current will lead the voltage in our circuit. Another term you're going to see is the cosine of phi. We do the cosine of this angle, it's adjacent over hypotenuse, so it'd be delta VR max over E max, which will end up reducing to R over Z. This is actually called the power factor. Because if you want to write the average power in terms of the source voltage, average power depends upon the RMS value of the resistor's voltage. If you want to write it in terms of the source voltage, you need to replace delta VR RMS with the RMS source voltage times the cosine of phi. So you can write it as this way. That is the RMS value of the voltage across the resistor. Cosine phi is called a power factor because you're only getting a certain percentage of the total maximum power that could possibly be delivered to the circuit. The maximum possible power that can be supplied to the circuit is when cosine of phi is 1, which means phi is 0, which means the current and the voltage are in phase with each other. The source voltage and the current are in phase. When can this happen? When can phi be 0?
No reactive elements.
That's one way, to have no reactive elements at all.
Or L and C cancel each other out.
Right. If XL and XC are the same, then we satisfy this condition. So either you can have no inductor and no capacitor at all, that's definitely the case. Or you can have XL equal to XC. Which, by the way, plugging in for XL being omega L and XC being 1 over omega C, that happens at a very specific angular frequency. That should look familiar. That was from the LC circuit when we talked about LC circuits before. This situation is a resonance situation. If XL equals XC, which is not always the case, but if it does equal, if XL does equal XC, we're a resonance situation, phi is 0, so this power factor is 1, so that means we're getting the maximum possible power for that particular circuit. If phi is not 0, if XL does not equal XC, then we have some other power being dissipated by the circuit. It's just not the maximum possible. So this is a special case. Not all circuits will experience this. So please don't try to use omega being 1 over the square root of LC for all of your problems, because it will not necessarily be.